Hello, in just a moment we're going to zoom in on the different sections of this whiteboard, but first of all I'd just like to welcome you to the combination series. I plan to have a total of 3 videos in this series, the second of which I focus on the method of stars and bars, and the third of which I focus on Pascal's triangle and the binomial theorem, and how those two concepts are related. But for this first video, I was just thinking of focusing on what combinations are, and just a few initial applications that we can use them for. So I think it's helpful to begin by explaining what combinations are and what they are not. Let's say I'm an administrator at a school, and I'm told by the school district to choose 4 different grade levels to administer a standardized test. And let's say that I can choose from grades 1 through 9. So one option for me to pick would be to administer the tests in grades 2, 4, 5, and 6. That would be one option, and the question here is, how many possible options could I choose? That is, how many ways can I choose 4 different grade levels to administer the test among the grades available to me to choose from, which are the grades 1 through 9. This is very different from the situation where we have 9 friends going to the movies together, and 4 of them choosing to go line up to get popcorn. In the latter situation, there's a sense in which the order of the friends in line matters. However, whenever we talk about combinations, or whenever we use the symbol with the parentheses that's seen on the board here, we are talking about situations where order does not matter. So a combination is just a particular collection of things from a larger set that doesn't have any particular order. And when we try to find combinations, we're trying to find how many ways we can have a set of a certain number. So it turns out that when we work out the solution for the testing question, we actually end up answering the movie theater question first. In fact, answering the movie theater question first is the best way to find our way to the solution of the testing question. So let's answer the movie theater question. There are 9 total friends to choose from to see who goes first in line. And then, once the first friend is already in line, there are now 8 friends to choose from to see who will go into the second position. Then once the first 2 friends are in line, we have 7 friends to choose from to see who goes in the third position. And then lastly, there's 6 friends to choose from to see who goes in the last position. So 9 times 8 times 7 times 6 is the answer to the movie theater question. Now, given any set of 4 friends, there's 24 ways to rearrange them in line. So this means we'll get our answer to the testing problem by dividing by 24. So in general, the number of ways to pick k objects from n is given by this expression. Note that in the testing situation, there were 9 total grades and 4 grades that we had to choose from. So in our example, the 9 times 8 times 7 times 6 corresponds to n factorial over n minus k factorial, and the 4 times 3 times 2 times 1 in the denominator corresponds to the k factorial. When computing combinations, it's important to note that the bottom number is always going to be factorialed in the denominator, and it's also important to see that the amount of numbers that appear in the numerator and denominator are always the same, and they're determined by the bottom number in the parentheses operation. Here's a very important tip. Never ever compute a combination where the bottom number is more than half of the top number. 100 choose 97 is equal to 100 choose 3. And this is because if we choose a collection of 97 things from a larger collection of 100, we're always leaving some 3 of them out. Therefore, every collection of 97 objects from 100 corresponds to a particular set of 3 objects from that same collection of 100. So therefore, 100 choose 97 and 100 choose 3 take on the same value. So in general, n choose k is equal to n choose n minus k. Our first application of combinations refers to handshaking. If there are 25 people in a room and everyone shakes hands with everyone else, there's going to be a total of 25 choose 2 handshakes that will occur. The next application has to do with the number of diagonals in a convex polygon. In this hexagon here, I've drawn all of the possible diagonals. If you count them, there are 9 in total, but there's a faster way to compute this number. So there are 6 total vertices on this hexagon. If we consider all of the possible ways that we can pair up two different vertices, we're going to get a sum that equals all of the diagonals plus all 6 of the sides. So if we calculate 6 choose 2, we're going to return a number, namely 15, that's going to include all the diagonals plus all the sides. So a trick to find the diagonals in an n-gon, just an arbitrary polygon that's convex, we just need to compute n choose 2 minus n. Here's one of my favorite applications of combinations. Let me ask you, how many rectangles do you think are in this figure where each vertex of the rectangle must be one of those dots and the rectangle is going to be parallel to the x-axis or the y-axis? So instead of counting them by cases, i.e. considering 1 by 1 squares, 1 by 2 rectangles, 1 by 3 rectangles, 2 by 2 squares and such, there's a much better method that involves combinations of what we just learned. In this particular array of dots, we have 6 dots going up and down and 7 dots going left and right. So it turns out that for any arbitrary rectangle that's counted in this problem, we can pick 2 points going up and down and 2 points going left and right to define the length and the width of this rectangle. For example, the rectangle that's shaded in the figure is defined by crossing out 2 points on the very first left column and crossing out 2 points that are on the last row. So I can define this rectangle's height based off of which 2 out of those 6 dots on the left first column I choose to define the height. So it turns out that there are 6 choose 2 or 15 different ways that I can pick 2 points from the first column to define the rectangle's height. And likewise, there are 7 choose 2 or 21 different ways that I can pick 2 points from the last row to define the rectangle's width. So that turns out to be 21 times 15 or 315 different rectangles altogether. And so in general, for an m by n array of dots, there are m choose 2 times n choose 2 different possible rectangles. So now it's time to present those that I'm coaching with homework bit 2, and of course anyone else can try this problem out as well. Your homework problem is essentially this: how many triangles are in this figure? Now for a triangle to count, all 3 of its vertices must be one of these points. Now if you find that 2 triangles are congruent but are formed by different sets of 3 points, you must count both of them. So if there's a bunch of triangles that are all congruent to one another but are formed by using different sets of 3 points, you must count all of them. Now the way that you arrive at your answer must involve combinations. And I have one warning. If you have a set of 3 points from this figure, but they all lie on the same line, or all 3 of them are collinear, that will produce a degenerate triangle, meaning that that will not count as a triangle. So make sure to consider that when you're finding your final answer. So a very common competition question is going to ask you how many total ways there are to rearrange the letters in a certain word. And when you rearrange the letters, they don't necessarily have to make another word, they just have to be a distinct way to rearrange the letters so that they're not the same arrangement. The best way to approach this problem is to think about it in terms of combinations. Let's place the 3 A's in our word first. Since the word Savannah has 8 letters in it, we need to place our A's in 3 different slots out of 8 possible slots. So we're faced with a question. How many ways can we put the A's into our 8 slots? We have 8 slots, and we want to choose 3 of them to put our letters in. How many ways can we do that? Well, that can be answered by computing 8 choose 3. Computing this in the way we did earlier, we get 56. So now we've taken care of the A's. We've placed them in the 8 slots, so that now we have to deal with the rest of the letters. When you're doing these problems, it's best to look at which letters are the most common first, and then move down in frequency. So let's consider the N's next. We have 5 free slots left to place the N's, and we need to choose 2 of them to put our N's in. So this amounts to computing 5 choose 2, which gives us 10. So in the beginning, there were 56 ways to place the A's in the 8 slots, and then we found out that there were 10 ways to place the N's in right after the A's. At this point, there are no more repeated letters. So at this point, all we need to do is figure out how many different ways can we rearrange these last 3 letters. And computing this last part should feel very similar to when we have 4 friends in line, how many ways we can rearrange those 4 friends in line. In that case, it was 24. In this case, since there's 3 letters, there's 3 factorial or 6 ways to rearrange them. Now we've taken care of all the letters, so we can conclude that the total number of rearrangements of the letters of Savannah is 56 times 10 times 6, which is 3,360. Here's a couple more examples of the same type of problem. Notice that I chose to deal with the letters that had the highest frequency first, and then moved down to letters with lower frequency. In the coconut example, you can either start with C or O, and in the Mississippi example, you can start with either S or I. In the Mississippi example, it's okay if you actually start by arranging the P's in first, but in all examples, you want to leave the unique letters for the last. Okay, those of you who I'm coaching, here is your third homework bit. Thanks for watching.